Start with work done by a force. The simplest case is, well, okay, you're carrying something like this, like my calculator, as you walk across the room. You are applying a force, I guess, pushing the calculator. Would you think of it that? No, maybe it's easier to think about lifting it up. Okay, you're lifting your calculator upward against the force of gravity a certain distance. The force you're applying is the weight of the calculator. That weight would be a force in newtons. I don't know. 2 newtons? I have no idea. It would be the weight of this calculator. It would be its mass in kilograms times 9.8 meters per second squared, times the distance you travel in that direction, say 1 meter. Okay, so if this is 2 newtons times 1 meter would be 2 joules of work done. And yeah, joules is the same as units of energy. More generally, for example, you might have a block of wood sitting on a floor, and you're going to push it across the floor. And maybe the force you apply is not parallel to the floor. Maybe the force that you apply is at that angle right there. What's the work done by that force as you move it across the floor by a certain displacement vector d? The work done turns out to be F dot d, the dot product of F with d, which by the geometric meaning of dot product is the magnitude of F times the magnitude of d times the cosine of the angle between them. There's the angle between them. It is a scalar quantity, and it is going to give you the work done in joules. It also could be thought of as being the component of the force parallel to d, dotted with d as well, or multiply the lengths, because if this is the component of the force, really the projection of the force along d, its length, its magnitude is the magnitude of F times the cosine of the angle by trigonometry. You got a right triangle there? Think SOHCAHTOA. The length of that force vector there, the hypotenuse has length magnitude of F. The cosine of this angle right here is adjacent over hypotenuse. Adjacent is up here, excuse me, over hypotenuse down there. Take the ratio of this to this, and you will, the magnitude of F will cancel out. You'll be left with the cosine of theta. But things get more complicated if the path of motion is not a straight line, but some curve. Maybe going all over the place. Maybe that's the path of motion. Whoops, I messed it up. That direction, going all over the place, starting at point A and ending at point B. And what's causing this motion? Who knows? But there's a force field in the background that is affecting the motion, at least. Maybe it's a gravitational field. Maybe it's a magnetic field. If it's gravitational field, it's affecting the motion of the mass as a mass according to the law of gravity. Though unless you were out in outer space, you wouldn't think it would have a big effect. I mean, the force vectors, the net force vector is, that we feel right here on the surface of the Earth is mostly downward toward the center of the Earth. But if you're out in outer space, this might be dominated by the sun's gravitational force. Or it could be a magnetic field, and that could be a charged particle. It's kind of hard to imagine. Why would it do this kind of motion? If it were a ship out in outer space, I guess there would have to be some thrusting going on to affect it this way as well, which of course the gravitational field doesn't have any effect on. But you can sort of ignore the thrusting that's going on. Just pretend for some strange reason it's traveling along this path in this gravitational field, and you can ask, what's the work done by the gravitational field on this particle? How do you figure that out? you may know you do an integral, you do a line integral of the vector field of f over this curve, this path here, C, is not just a curve, a parametric curve, not just a path, but an oriented curve. I guess in calling it an oriented curve, I mean, you're saying it has an orientation. There's arrows showing a direction. That happens with parametric curves as well, when we assume time moves forward instead of, say, backwards. That's the motion as time increases. And yeah, you do a line integral of f over this curve, is what you end up doing to figure out the work. Why? Imagine zooming in on a small piece of the curve, say right there. I mean, I've made this be a fairly large chunk, but imagine it's infinitesimally small so that it looks straight or almost straight. I'll make it slightly curved. We're zooming in there. And imagine a small amount of time that's gone by. And in fact, technically speaking, to be a correct way of thinking about it, you want to imagine this curve is parametrized by arc length, just like last Friday, S. So effectively, S is the same as time. It's like you're traveling at 1 meter per second, say. Of course, in space, that wouldn't happen. That would be way too slow. But just for the sake of argument, pretend you're traveling along this curve at 1 unit of distance per unit of time. I mean, if you change your measurement units, you can always do that. You know, maybe it's 1,000 meters represents 1, and okay, 1,000 meters per second corresponds to 1 unit of distance per unit of time. Imagine breaking it up into tiny chunks, and imagine this arc length being called ds for a small amount of arc length. Back in, at the beginning of the course, we had a parametrization, R of t. Well, I could call it R of s here, calling it an arc length parametrization. But no matter what kind of parametrization we make, we can create the unit tangent vector. I'll just call it capital T, and I won't say what the variable name is. That would be in the direction of motion and tangent to the curve. If I multiply that unit tangent vector by ds, I'm going to get an infinitesimal tangent vector, so to speak, that would look about like this. Of course, this picture is not accurate. I'm drawing all these vectors, so none of them are being drawn in an infinitesimal way, because it's impossible to draw an infinitesimal. You only need to use your imagination and just pretend these things are infinitesimally long. T has got unit length, unit 1 length. It's not infinitesimal, so it's a little bit misleading in terms of the picture. That would be an infinitesimal vector. The book calls this D. And the question then would be, what's the small amount of work done by the force field over this tiny amount of time? The force field, F, is probably some much larger vector even. But the principle of the tiny amount of work done over this tiny amount of time, or tiny chunk of the curve, is the same as up here. Do F dot D. Take this force vector and dot it with this infinitesimal tangent vector, you might say. You could call that tiny amount of force dW. Hey, Arthur, for a small amount of work, it's a small amount of work over a small chunk of the curve, F dot D. But what is D? It is TDS. So the total work done then is an integral over the curve of these dW values. Why? It's hand-wavy math. No rigorous math going on here. In a sense, it's kind of like a definition, but intuitively we're imagining the total work is the sum of the little works. And that, if you haven't done the reading all semester, say, that's how the author describes it. And I would recommend, even if you haven't done the reading all semester, starting to read now. because the author does try to give you some insight into how to think about these things. The total work is the sum of the little works, which is this kind of sum. But just like with double and triple integrals, when we wrote them in an abstract way, there's no clear way to evaluate them. This is maybe somewhat clear, somewhat as an abstract idea, but how do you actually compute it? Just like with the scalar line integrals from last Friday, you need a parameterization, you need an R of t, and that's going to be helpful. But it's also going to be helpful, it turns out, to write this abstract version of this line integral in another way. So again, let me rewrite it here. We've got the total work done is ultimately this integral. But given a parametrization, given r of little t, we know how to figure out capital T of little t. It's the derivative of r of t, the velocity vector, divided by the speed, the length of the velocity vector. We also saw last Friday, ds dt, the derivative of the arc length with respect to time, is the same as the speed. So we could also write ds is the speed dt. And you can imagine this to be a product if you like, though in the end, when we do the integral, it's not literally a product. But for the sake of imagination, the sake of conceptual understanding, you can pretend this is a product. This is effectively distance equals rate times time. ds is how far you go in this tiny amount of time dt when you're going at, say, approximately constant speed equal to the length of r prime of t, the length of the velocity vector at that moment in time. So using these ideas, we can make some replacements and rewrite this integral by replacing capital T with r prime over the length of r prime. I'm suppressing the t's, the little t's, times the length of r prime dt. Cancel those things, and you end up with the integral of f dot r prime dt. And it's also common to write that as f dot d vector r. Kind of crazy, just a bunch of different ways of writing it. But the most useful way of writing it in terms of evaluating the integral is this way. Because with that one, you're going to actually have limits of integration for t that you can plug in and do the integral for. This one's ultimately going to be done a little bit more explicitly as the integral from, say, a to b of the vector field f evaluated at r of t dot r prime of t dt. And then it becomes an ordinary integral to do in the ordinary way. And it turns out, typically, it's easier to do this integral than the integrals from last Friday, at least the ones that were not trivial. Remember the ones from last Friday, we had to integrate little f of s, and ultimately we had to, by using the parameterization, we needed the magnitude of r prime in there without canceling it like we did here, which means in the end you needed typically square roots involved, and you had non-constant functions under the square roots. And you, at least a couple problems, you had to use Mathematica to do it, or your calculator. Setting up the integral and not being able to do it by hand, relying on technology to approximate it. This one you almost always can do fairly easily by hand, though often trig identities are necessary to use. Especially when you're parametrizing over, say, a circle or something. But it gives you the work done. And it doesn't matter what parametrization you use. That takes proof. I'm not proving it. Any R of t for the given oriented curve will work. Okay, as long as it's truly oriented, as long as it's truly tracing out the curve in a single direction and say not going back and forth, for example, which does happen with some parametrizations. You want it to tracing out the curve in the indicated orientation with the indicated arrows in your drawing or described in words. But anyone will work. Let's do an example. We'll typically keep our vector fields fairly simple. I think this is the example from Friday. Let's let f equal negative yx. And let's say the oriented curve that we're talking about is the upper semicircle of the unit circle, oriented counterclockwise. So there's 1, 0. Here's negative 1, 0. C is the upper half of the unit circle with the indicated orientation going counterclockwise. If this were a force field and you had a particle moving from here to here, the integral we're about to do would give you the work done by the force field on that particle. Not worrying about why the particle is moving as it is. Again, it could be a mass in a gravitational field, and then yes, the gravitational field would technically affect the motion. It could be an electric charge in an electric field or magnetic field or whatever, and that would be affecting the motion. Why would the motion look like that? Don't worry about it. It's kind of like with the fluid flow. We leave that for the physicists and engineers to worry about what's practical. We're thinking about other possibilities here to open our mind, expand our mind, and ultimately still apply it to physics, but it's not always clear how. But we can still enjoy doing it. We need a parametrization. Let me, in fact, do 2 parametrizations and show you that we get the same thing. I'll use R1 of t to be the simplest parametrization, cos t sine t, as t varies from 0 to 2 pi, or 0 to pi, excuse me. Another parametrization we could use, though, if you think about it carefully, would be, for example, let's go 1 minus t for x and square root of 1 minus t squared for y as t goes between 0 and 2. I claim that's another parameterization. Where did I get that from? Well, the equation of the unit circle is x squared plus y squared equals 1. If you solve that for y, and you want the upper half of the unit circle, it would be y equals positive square root of 1 minus x squared. If x is 1 minus t, which is a quantity that starts out at 1 when t is 0 and goes down to negative 1 when t is 2, then I'd have to use this equation to figure out the corresponding y by replacing x with 1 minus t. Of course, you could simplify this. FOIL that out, subtract it from 1. The 1s would cancel. Get a positive t squared there, but with a minus sign. Negative t squared, and then it would be a plus 2t, I believe. Would be what that equals if you simplify it. Probably this one's easier to do by hand, but let's see what happens. We need R1 prime. We need the velocity vector. Derivative of cosine is negative sine. Derivative of sine is cosine. We also need to evaluate, if you look at this expression right up here, we need to evaluate f of r of t. F of r of t, effectively plugging in the parameterization, it's an R1, into f. It's written with pointy braces here in vector form, but when I plug it into f, maybe I prefer using parentheses around the cos t and sine t. I don't have the parentheses over there, but remember, it's because they're just always suppressed. I certainly could write this as f of xy. So I'd want to replace x with cos t and y with sine t. And looking at that formula, I'd get the vector negative sine t cos t. And once again, looking at this formula, I'm going to need to dot those things before I integrate. So find the dot product of these two things. F of R1 of t dotted with R1 prime of t will be negative sine t cos t. R1 prime turns out to be the same thing. We're really dotting a vector with itself here. In the end, giving us positive sine squared t plus positive cos squared t. Hey, our favorite thing in trig, that always equals 1. So the integral ends up being very easy to do. The work done, if I think of it as work, is the integral ultimately from 0 to pi of 1 dt here, which is going to be pi in the end. Pi joules. About 3.14 joules if we use standard units. Force would be in newtons. Distance would be in meters. If that's the case, then the work done would be in joules. Does the other parameterization give us the same thing? It should, though it's not obvious that it will. How much can I do by hand? How much do I want to do by hand? Let's find the derivative. First one's not so bad, just a plain old -1. Second one, I need the chain rule for. This is negative t squared plus 2t to the 1/2, so the 1/2 comes down. Let's write it as 2t minus t squared in there to the negative 1/2. Don't forget the chain rule times 2 minus 2t. I'm almost out of room. You see that okay? That's a 2t minus t squared, all to the negative 1/2, and then times outside that 2 minus 2t. The 2's can cancel with the 2 there. I could ultimately write this, it looks like, as 1 minus t over square root of 2t minus t squared. Minus sign there. Yeah. How's this going to work out? I got to plug these things into F. Well, I need to plug R2 itself into F. And then take the dot product with this thing. Let's go ahead and do it. What's F of R2 of t? Dotted with R2 prime of t. That's F of R2 as first component 1 minus t. Looking up here. Second component, square root of 2t minus t squared. That's got to get dotted with this vector. Careful, it's tempting to ignore the F and just dot those. Like, oh, the square root's canceled. But that won't happen right away because I got to use the formula for F. Which is, again, negative y comma x. Oh, unfortunately, now the square roots will not cancel. Negative y comma x is what that is. Dotted with this. Get a positive square root of 2t minus t squared when I multiply those two things. And then here, the 1 minus t's becomes squared. But that square root in the bottom is not going to go away. Probably should continue simplifying, getting a common denominator equal to the square root. So it would be 2t minus t squared. I'll go ahead and expand this. So why not, I guess. I'll do it, see what happens. Expand that, I get 1 minus 2t plus t squared. I will get some cancellation. Looks like the 2t's will cancel. The t squared will cancel. And we ultimately end up with 1 over square root of 2t minus t squared, which doesn't seem so nice as far as something to integrate. In fact, if we're integrating this from 0 to 2, technically it's an improper integral. Oh. Is the work done going to be the integral of this from 0 to 2? Technically, if I haven't made a mistake, it should be. Is that a doable integral? It wouldn't surprise me if it is, but it's not clear to me how to do it offhand by hand. Let's just see if Mathematica can do it. Technically, again, it's an improper integral because you'd be dividing by 0 at both t equals 0 and t equals 2. Is it even a convergent improper integral? Evidently, it gives the right answer. I don't know how you do it by hand. Can we even find an antiderivative by hand? Yeah, I guess so, but it involves a logarithm in kind of a complicated way. I don't think I'd want to do it by hand. But I am happy we got the same answer, showing you math is consistent and I didn't make a mistake. Evidently, that is the integral to do with that parameterization. And the answer, once again, is pi using Mathematica. Okay, so the parameterization doesn't matter, but some parameterizations are much easier than others. We should also interpret the meaning of this. What's the geometric meaning of what we just did there? If I make a vector plot of the vector field, negative yx, this was one of the examples from last Friday. This one's the one that has rotation to it, like that. And again, it's really a direction field instead of the true vector field because we're not seeing the correct lengths. But the more orangish, yellowish vectors are longer than the darker bluish purple vectors in the true vector field. Let's zoom in near the origin. Not too far though. Tell it was a difference, but yeah, it is different. Where is our parametric curve? Use parametric plot. I'll use the cosine and sine one. He goes from 0 to pi. There it is. Notice, since we're going around counterclockwise, the unit tangent vectors that we would get in our imaginations here would be parallel to the vector field, no matter where you are. The vector field is tangent to the curve. The dot products that you get, f dot capital T, would all be equal to the magnitude of f. F dot capital T. F dot capital T here is the magnitude of f times the magnitude of capital T times the cosine of the angle between them. That's always 1, though. It's a unit vector. So we get the magnitude of f times the cosine of the angle. But if F, the vector field, this rotational kind of thing, is always tangent to the curve, that angle is going to always be 0. Capital F and capital T are parallel and pointing in the same direction. The angle is always 0. The cosine of 0 is 1. You're effectively just integrating the magnitude of F over the entire curve. Moreover, with this particular vector field, the magnitude of F along circles centered at the origin is constant. Why? Magnitude of F along circles centered at the origin here for this vector field, negative yx, its magnitude is the square root of negative y squared plus x squared, same as the square root of x squared plus y squared, same as the magnitude of the vector xy. At any point along a circle centered at the origin, the magnitude of xy, thinking of it as a position vector, to that point is going to be constant. It's going to be equal to the radius of the circle, in fact. So the magnitude of F itself is also equal to that, the radius of that circle. It stays constant. You're effectively integrating a constant when the magnitude of F is 1, if we're on the unit circle, we'd be integrating 1 from 0 to pi. And that's what we did with the simpler parametrization and got an answer of pi. Yeah, different parametrizations give you more complicated integrals, but you can think of it this way and get the same answer. But this is only because the magnitude of F is constant along that semicircle centered at the origin. It's a special case, but it's kind of a nice special case.